Let us now look at part B. Here, a student is expected to answer 5 questions out of 10. Even here, there is a lot of choice. So, first question, which is 16th one in the series, says write any two differences between polar and non-polar molecules. Given here, in case of polar molecules, it has a permanent dipole moment. Just learn these facts. It's not worth to explain these things now. In case of non-polar molecules, it has no permanent dipole moment. Just think that known as no is no here. That way it will be easy to understand. Again, difference is it is heteronuclear. This is homonuclear. Hetero means different atoms will form a molecule. Example is HCl. There is hydrogen plus chlorine which form molecule. Here it is two oxygen atoms forming a molecule. Since the molecule has same types of atoms, it's called homonuclear. Homo means same type, hetero means different types. Remember, at least 2 points. Remember the first 2 points. 17 says state Ohm's law and write its one limitation. This is a very important question. The question could be asked in many ways. Sometimes they may ask you state and explain Ohm's law itself as a 2-mark question, or question could be just write limitations of Ohm's law as a 2-mark question. When combined here, we look at it more elaborately. So first, the statement, as I told you earlier, when it comes to laws, just learn the laws the way it is. It says with temperature and other physical parameters of a conductor remaining constant. This temperature should remain constant and also other physical parameters should remain constant. Then the current passing through a conductor is directly proportional to the potential difference across the ends of conductor. A very important statement. So we'll look at a case where the question says to state and explain Ohm's law. If that is a 2-mark question, then you all can write the statement given here and explain this. So what is given is the current passing through conductor is directly proportional to the potential difference. Actually what it means is that it means I is proportional to V, but books don't write this way. For some reasons books state it this way and write V is proportional to, even though these two would mean the same. We solve them mathematically, it remains same, but physically they are two different meanings. But books write this way only. There are many instances where books define one way and write another way. Another example we can say is that if we look at Newton's second law of motion, it says the rate of change of momentum is directly proportional to the applied force and the change takes place in the direction of applied force. But books write like this mathematically, which is opposite of the statement. Remember, there are many instances where it has been defined in one way, written some other way. Just remember this fact also. Here, even though we define saying that the current passing through conductor is directly proportional to the potential difference, we write this as saying V is equal to, now we need to remove this and bring in a constant. You can say V is equal to V into R, where R is called a constant of proportionality called as resistance. The question says for 2 marks, state it and write till here saying R is the constant of proportionality called as resistance. But in this case, it says write one limitation. As I told earlier, limitation itself could be asked as a 2-mark question. So at least learn 2 limitations. Here 1 is sufficient, but at least learn 2 because this could be a 2-mark question. The first one is already given here. If we look at the statement of Ohm's law, it says with temperature and other physical parameters remaining constant. So Ohm's law is not valid if temperature and physical parameters don't remain constant. See, first point. Second point is it is not applicable to semiconductors. There are many more differences, but this is sufficient. 18 says define magnetic declination and inclination of the earth. We first define this. Just learn the statements, because this is an important statement. It's not worth to explain this fully. Magnetic declination is the angle between geographic meridian and magnetic meridian. Second point is angle of dip. It is the angle made by a magnetic field about horizontal. Just quickly explain this. As given here, suppose if we consider Earth's surface like this, there are two poles called as North Pole and then South Pole. This is called as geographical North Pole and geographical South Pole. Also, there are magnetic poles. So the magnetic poles is like this. This is called as magnetic south. This is called magnetic north. But some books write there, and also some books write this as magnetic north and south. But don't worry about the reason. The reason is not required here. So this is geographical south. This is magnetic north. We have four poles. Two poles for geographical poles and two for magnetic poles. Now suppose if you want to find at this place what is the declination. So we need to draw a meridian, a line or the circle connecting the two poles. This is called as geographic meridian. That is a circle connecting two poles called as geographic meridian. Similarly, a circle connecting two poles, that is magnetic north pole and south pole, is called magnetic meridian. It will be like this. Just read out this. So here we add the geographic north pole. Example thing near the Arctic. This is geographic south pole, and then there's a point here very close to this called as magnetic actually south and magnetic north. Suppose at this point we want to find what is declination. So we should draw two circles. One circle connecting magnetic south and magnetic north. That will be something of this kind. This is called as magnetic meridian. We want to find at this point only. Similarly, we can draw a circle, a great circle from geographical north to south. That circle will go like this. Draw it properly. This angle made here called as magnetic declination. This is what is declination. It is the angle between the two meridians in simple language. Next is inclination. Now suppose if we hang a bar magnet like this, now this will not be straight. It depends on the place. Suppose if you hang it like this, imagine that the magnet will bend like this, means it points in some direction. So if we have horizontal like this, the angle made between horizontal and how a magnet is pointing, this is called as inclination. Just remember these two definitions. 19 says draw a typical hysteresis loop for a ferromagnetic material. Mark coercive fields in it. as given here. So this is a graph for V versus H. Just learn this graph. So what is seen is, to understand this, suppose imagine that we have magnetic material and we place it in a magnetic field. For example, think of a ferromagnet. If we place a ferromagnet in a magnetic field like this, then what happens is the dipoles will be aligned along this direction, said to be magnetized. What you find here, when we increase the applied field, it will be more and more magnetized. It won't be a straight curve, it's something of this kind. At this point, it is completely magnetized. How much ever the field applied increased, it will be more magnetized. Now suppose if we decrease the magnetic field, example, imagine we are varying this H from 0 to say 20 Gauss. This 20 is very big number. Just to make it sense, we're given 20 as a number here. Suppose you decrease it, and then if you go back to 0, then what we expect is, we expect these should be again in different directions. Because we expect the dipoles to be in different directions so that it becomes 0. That is, net might become 0. But what happens is, even though the applied field is removed, there is still some magnetization existing in the material. That is shown by this point B. So, even though when H is increased, we expect the magnetization should be 0 in the material. So it started off with, when the applied field was 0, the magnetization, the material was 0. But when you go back, it doesn't become 0, which means this material has some magnet left in it. That is given by the point B. Suppose if you want to remove that also, this is called as retentivity. Suppose if you want to remove that also, we need to make the field in different directions. Earlier, the applied field was pointing from left to right. Now we need to reverse the field like this. In that case, when we reverse the field, these dipoles will try to align in this direction. So the dipoles have been aligned in this direction earlier. Suppose when we decrease the magnetic field, they'll have different orientations but not net 0. If you decrease the field, these dipoles want to orient from this to this orientation. At some point they'll cross 0 also. So at some point they'll cross 0. That value of the applied field is called as coercive field. So coercive field is the field for which the magnetization in the material is 0. So here, for the field values at points C and F, that is for OC and OF, these are the field values for which the magnetization material is 0. This is called as coercive field. This is called as retentivity. So O to B or O to E is called as retentivity. O to C or OC or OF is called as coercive fields. Just learn this diagram. 20 says, what is displacement current? Write its expression. Now, to define this, we can say is the current produced due to changing electric field. Now, until now, what you learned is, you learned that the motion of charges give us current. But here, even though charges do not move, there can be possibilities where change electric field itself will move charges. So the current which is produced due to changing electric field is called as displacement current. Learn this very important statement. This is quite important question. And its expression, it's given as ID. So ID is equal to naught into d phi e by dt, where phi the electric flux. You can write flux as E dot A or just E into A. So if you read as this, epsilon comes out, A comes out, what remains is d by dt. So even this sufficient, you can write this also, both are equivalent only. Just written phi as E into A. So here we find there is rate of change of electric field. So this will give a current called as displacement. 21 says write the two conditions for total internal reflection. The two conditions are very important. The first condition is the ray of light must travel from a denser to rarer medium. A very important question. Second one is the angle of incidence must be more than critical angle. So these two are conditions for total internal reflection. Just here also learn to what is total internal reflection, or the term could be asked here is to define what is critical angle. These two are important terms. Just do it quickly here. If we have a boundary like this, and we have a source of light somewhere here, example, this is point O. If we look at light rays, this light ray will move undeviated like this. Let us consider this as denser medium and this as rarer medium. If a light ray falls at an angle to the normal, this light ray would bend away and go like this. So if we draw more and more light rays, as I is increasing, R also is increasing, and we know that when light moves from a denser to rarer medium, light would bend away from normal. So there will come a point where this light ray will bend so much that the refracted ray may move on the surface. That is, if you draw more light rays, it bends away, it bends more and more away, it goes like this, it bends more and more away. So there will come a point where the refracted ray moves on the surface. So this angle here is called as critical angle, such that here the angle of refraction is 90 degrees. You can say critical angle is the angle of incidence for which the refracted ray moves on the surface. Even this could be asked as a 1 mark question. Or if the angle of incidence is more than that, because the more and more light moves far away, if you compare this case or this case or this case, the angle is more here. So this angle we call some I dash. This I dash is more than critical angle. In this case, the light would be totally reflected back. This phenomenon in which the light is reflected into same medium is called as total internal reflection. Remember the definition of it and also its conditions, very important. 22 says write any two use of polarites. Just learn the uses. They are used as polarizing sunglasses because many sunglasses will have in it polarites, and these are also used in making or viewing 3D films. Just learn these two definitions or the two uses. 14 says find the potential difference through which an electron be accelerated so that its de Broglie, in G silent here, de Broglie wavelength becomes 0.1227 nanometer. Now again there's a formula for this, just learn the formula. The wavelength of an electron when it moves between a potential difference given as 12.127 angstrom by the root of G. This is formula to be memorized, where 1 angstrom is equal to 10 power minus 10 meter. Here question says what is the potential difference, which means we should find what is V from here. So from here we can say root V is 12.127 into 10 power minus 10 by lambda, because here lambda is the wavelength, is equal to 0.1227 into 10 power minus 9. Here it goes 100 times, and this goes 9 times. So what remains here is root v is 100 into 10 power minus 1, because this factor is 10. Root v is 10, or v is equal to root of 10, that is equal to be around 3.162 volt. 24 says write any two limitations of Bohr's atomic model. Again here at least learn 3, because sometimes this could be asked a 3-mark question. The first limitation is it is applicable only to hydrogen or hydrogen-like species. Example, hydrogen atom or He plus or Li2 plus, etc. All this contains only one electron. So these are called as hydrogen or hydrogen-like species. Can't use this formula for lithium atom, only for lithium ion, which has been useful. So one drawback is it is applicable only to hydrogen or hydrogen-like species. Second one is it does not explain the reason for intensity spectral lines. Sometimes what happens is some lines will be more brighter, some less brighter. So it doesn't tell why the intensity is varying. The third point is it does not explain Zeeman effect and Stark effect. Just learn these names. There's no need to go and understand why it is this way. Just learn the names. Again here one more question could be, which is more important, to learn the postulates of Bohr's atom. I'll take up this in the next model paper. Those who are interested can go and learn this. Even this is a very important question, otherwise the video becomes very long. 25 says in the equivalent circuit, if A is equal to 1 and B is equal to 1, what is the value of Y? Name the equivalent logic gate that this circuit represents. There are two gates given here. This gate is the OR gate and this is the NOT gate. Both A and B are given input of 1 1, which means the high and I given here. For a OR gate, the output is I even if one input is I. That is, if you have 0 and 0, all A, B and Y will be 0. If 0 1, it will be 1. 1 0 1. 1 1 B. This is the output. The output is high in an OR gate even if one input is high, because it's an OR gate. OR means either of the two. So common meaning of English OR. So if either of the two, here this is 1, output is 1. Here this is 1, output is 1. Here both are 1. Even then output is 1. It is not 2 here, it's meaningless because the values here is either 0 or 1 only. Output is 1. Now the output, which is 1, is given to a NOT gate. NOT gate would be its complementary, which means if it's low, output is I. If input is 0, output for NOT gate would be 1. Input here is say A, output would be A complementary. The output is 1, when input is 1, the output becomes 0. So here, since 1 is the input to NOT gate, what comes would be 0. Here it is, answer is 0. The question says name the equivalent logic gate. Now these two can be combined into single gate of symbol like this. This is called as NOR gate. That is NOT gate plus OR gate together called as a OR gate, and this its symbol. It's A here and B here. The output is, for an OR gate it is A or B, but Not means complementary. So it is A or B which has been complemented. So it becomes A or B, the whole complement. So this is the equivalent